your grading scale? Like how it's like the.
I think so. I think I changed that. If it does not, if you have any suspicion, just let me know.
Okay.
Yeah. I just changed my password this morning, so.
I hate how frequently you have to change it. I hate how frequently you have to change the password for the system. This is, for student staff is the same as like faculty and everything.
Yep, every 3 months.
Yep.
But you can change just a part of it.
Yeah.
Yep.
You got the exam in hand today?
Yeah, the exam is in one of the bags. Oh, right here. I think it's this one. I opened the other one, it's the wrong class. So it's gotta be whatever is left. Right? Yep, that's the one. I'm gonna just start it from one side, so it would eventually get out to the other side.
Okay.
There's no marking on the exam as usual. Okay, so because I just do all the grading online. I graded 2 questions out of the 5. So if you're getting a really low score at this point,
Yeah.
no worries. There are 3 more that I'll be grading. Okay, so let me check. It's recording. Good. And the voice is also connected. Good. Okay. So what we'll do today, or what I'm going to do today first, is to go through the homework assignment, just so that we know what the trace is supposed to look like. There's not a single way to do it because there are a few cases where there are ties. So depending on which one you choose to proceed with, you can have a trace that looks different from somebody else's trace. All right. So this is the graph, and I'll try to come up with a way to kind of track this down, and be able to show how things are updated at the same time, which is going to be a little bit hard because do you want to use the table way or do you want to use the kind of graphical way? It's up to you. Table? Okay.
Table.
We'll use table then. Okay. Because you can use the graph way too. Sometimes it looks a little bit easier, but it's up to you. Yeah, but then you have to update, like cross out things, so, yep.
On the final, which way will we use it? The table or the graph?
The table way leaves a better and more complete trace for me to look at, so I can see whether you know when to update which vertex. So I think the table way is a little bit better. This homework assignment one, is actually not as bad as the one that we talked about last week, because there's no one single vertex that has to be updated twice, if I remember correctly. Whereas the case that I created last week intentionally was to illustrate how a vertex can be updated. Even though a path was found, it wasn't the shortest one. We found a shorter path later on, so that was actually a little bit more complex. Yep?
There's still one part in one line of the algorithm that isn't quite clicking for me.
Okay.
It's a variable u.
The variable u.
It seems to be introduced without any.
Okay, so let's clear that up first. Okay, so we are looking at this u here, right? Okay, so this part is basically saying we are removing edges that goes from w to whatever to anything from e prime, but only from e prime. So we leave e alone, and all the operations are being done to e. It's basically just erasing what we thought was part of the shortest path from W to one of the destinations. We take that out because now we know that was not the shortest path. So that's basically what this step is doing.
So that right there will take out multiple.
It should only take out one and only one, at the most one, I should say. It should take out at the most one, because remember, E prime is always going to be a tree, which also means there's only one edge going out of each vertex, up to one. So that's why this code here really should not have multiple edges to remove, but I can make it more general and just say that, okay, whatever number you find, get rid of all of those.
Okay, that makes more sense.
Okay. Cool. So it's good to get that cleared up. So I'm going to create a document in the share folder, just so that this way it is already in here. And I'm going to use a Google spreadsheet. Yep. Go ahead.
So every time I try to access the share folder link, I'm only seeing like 2 files. I don't know if that's, and I tried like logging out on my apps account to see if that was like messing with it, but.
You mean this one?
Yeah, like when the link that you have on Canvas, it only shows like 2 files. I haven't been able to see any updated files.
Try that. Okay, let me see if I gave you the wrong link here. Okay, open view.
So I'm wondering if like maybe the permissions are set on certain files or.
You are right. Yeah. This one is shared. Oh, that's because this one is a class-specific share and not a whole class share. So I need to give you the other one. Okay. Gotcha.
I think it worked for me. At some point I had a link that worked, but yeah, now it's not letting me see anything.
Okay, so I'm going to give you this one here. Okay. So I'm going to update this one to that one. Or I'll just add a new one. There we go. We'll add a new one. Non-semester specific share folder. Okay, that would make it clear. There we go. So give this one a try. I'm just, I just published it, so you should be able to see it now.
Yeah, I'll give it a try.
Okay. And I'll rename the document to the Dijkstra's algorithm trace. There we go. Okay. So we got a few ways to do this. Okay. We can switch between the tabs, or we can just, we'll try to switch between the tabs and see how well that works. If it's too confusing, then I'll try to display these two side by side.
It works.
It works. Okay, cool.
Yeah,
thank you.
you.
All right. All right, so this is the graph that we are dealing with. And okay, I think that's the entire graph. I was making sure that I don't have anything to the left because the cropping tool that I used I didn't use it exactly the right way, and it seemed to suggest that there's something to the left, but no, that this is the entire thing. All right, and then the algorithm itself is right here. Okay, so there are 3 things that we need to look at the same time. One is the algorithm, one is the graph, and one is the actual trace. Now, hopefully, once we kind of look at the algorithm enough times, we kind of know what it's supposed to do, and so we don't have to keep referring back to the algorithm. The trace that we are doing here, I do not need to do a full trace. When I taught cisp440, I make my students to do like full traces for every single algorithm, which is line by line. This one is not quite line by line, okay? So it's not, hopefully we don't have to go back to this too often. So I'm going to move this one over here, so the last 3 tabs in the browser are the ones that we need. All right, so according to the homework assignment, okay, I'm scrolling down just a little bit here, the destinations are vertex C and vertex E, so we do need to know that. Okay, so we were just passing the exam 2 around, so if you have not gotten your exam 2, this is, it's here. Okay. We can pass it around again. All right. So in the trace, okay, so in the trace, the minimum columns that you have to track would be Q, E prime, and then all the L values. So we got the L value of A, the L value of B, C, D, E. I think we have all the way up to G, so F and then G. Okay. And these do not need to be that big, so I'm gonna shrink these columns because they're all pretty easy to track. Q and E, especially E, can take a lot of space. Q doesn't take up a lot of space, so that should be fine. E probably need a little bit more space here. And I also mentioned last week that when I assigned the homework assignment, it might be helpful to track V and E, because as your algorithm go, you might want to go like, okay, which vertex am I tracking at this point? Okay, so V can be useful, but you're not required to track V or E. E in lowercase. That's basically the edge that we're looking at that goes into vertex V. Okay, but having these can be helpful, just so that as I keep track of the algorithm, I can figure out, okay, which edge am I tracking, which V am I tracking. Okay. And I also mentioned that the initialization can all be done in one single row. Okay, so there's no need to separate the initial steps. In other words, everything that goes from here to here, we can just do it in one single row. Okay, so all of these can be done in one single row. So we look at the graph here. We have 7 vertices. 2 are the initial, or 2 are the destinations, vertex C and vertex D. And it does feel a little smaller. The power seems smaller now. Okay, so vertex C, which is here, and vertex Z are marked as our destinations. So they are the only ones with an initial L value of 0, and everybody else start with L values of infinity. We also want to we also want to put vertex C and vertex Z into Q to start with. E prime as a set of edges is starting off as an empty set, because initially we do not know whether the vertices are reachable or not. So we just say, okay, we will make it an empty set. So that's exactly how we're going to initialize Q, which is CE. E is an empty set. And all the L values except for C and E are infinity. Okay, so I'm just going to spell out infinity instead of trying to use the symbol. C is the one that starts with a 0, and so is E. There were a few people, or at least one person, talked to me about how most of the other algorithms can only handle one single destination. Okay, so what I'll do is I'm going to show you that every single algorithm can track multiple destinations. It really is just a way of presenting, what is multiple destination. So I'm going to kind of digress a little bit here, just so I can show you what I mean by that, because I think it is kind of important to talk about that. Yay, okay. So when you have a single destination, okay, so let's say this D here is my single destination. So to emulate multiple destinations, or if your algorithm can only deal with one single destination, but in reality you do have multiple destinations, this is how you do it. Let's say the actual D1, D2, and D3 are the actual destinations. But your algorithm says I can only deal with one single destination, vertex. It's easy. Make these edges 0. So now you have three virtual destination vertices. So the same algorithm that can only start with one single destination vertex can now say, okay, we have multiple destinations, and the rest of the algorithm should still work. Is that okay? So in the example of the park and your bathrooms, it is almost the same as saying that there's actually only one single bathroom, but there are multiple portals in the park to the one single bathroom, as opposed to multiple actual bathrooms.
And so in this case, there's 2 bathrooms.
Huh?
In this case for the assignment, there's 2 bathrooms?
Yes.
Okay.
So in the case of the homework assignment, you can look at it as having 2 actual bathrooms or 2 portals to the same bathroom. And the location of the portals would be the D1 and the D2 and the D3s. Yep.
And just to confirm, we don't care which bathroom we end up at, as long as we end up at a bathroom, right?
That is correct.
Okay.
Yep. You just have to go to the shortest bathroom, the bathroom with the shortest path. And that's the important part. Just ask any kid in in a theme park. Yep.
What if there's a vertex in between the two destinations?
A vertex between the two destinations.
Yeah, like in between D2 and D, we have something in between that's connecting them. We can't say it's 0, right?
Okay, so it depends on how, quote unquote, it is in between. So let's say we have a vertex A here in between. So can you tell me what edges we are talking about? From which to which?
Like say D2 to D.
To A to,
Like suppose we want to go to D2.
Uh-huh.
Going to D, but A is the one that's in between. There's no direct path from D2 to D.
there's no direct path from D2 to D.
It goes through A. It goes through A.
It goes through
If
A.
you need to get to D from D2, you have to go through A.
So A is in between D2 and D.
Put A between,
A is in between D2 and D.
okay, so we have this scenario, like that. And what is the cost of the edge from A to D?
2.
Well, then D2 is not having a zero cost, path to the destination. It's not a virtual destination anymore. Because the idea that I was trying to talk about is D1, D2, and D3 in the original graph are quote-unquote virtual destinations. So even though there's only one official destination, which is D1, D2, and D3, they all have zero cost edges to the one destination. So that will make these virtual destinations. In other words, if you have an algorithm that can only deal with one single destination, you can just do something like this to make it handle the cases where you have multiple destinations. Yep.
Would it make sense somewhere to say that D is the virtual destination and D1, D2, D3 are like the physical? And then
Yeah,
D is
sort
like
of.
the
It depends on
virtual?
from whose perspective.
Yeah.
If you look at it from the perspective of the algorithm only knows D as quote unquote the destination. So that will make D1, D2, and D3 the quote unquote virtual, non-official destinations. But from the opposite perspective, which is the application of that, then yes, D1, D2, and D3 are the actual destinations. You're coercing the representation so that the algorithm would work. So that would make D the virtual destination. So I guess it depends on your perspective, from the algorithm's perspective or from the application's perspective. Okay, but very good point, nonetheless. Is that okay so far? Because I know some of you are taking cisp440 or have taken cisp430 where they talked about Dijkstra's algorithm. And there are many Dijkstra's algorithm implementation where they can only handle one single destination. This is how you can massage the representation of the graph itself to handle multiple destinations. Which makes sense, right? Because a lot of times there are multiple places where you can say, okay, this is where we want to be. I just need to find the shortest path from a single vertex to any one of these. It doesn't have to be a specific one. So this is how you can, kind of emulate that effect using any algorithm that can track only one single destination. Is that okay? All right. Okay. So getting back to here, we are done with all the initialization. V itself doesn't take a lot of space because it is a single vertex, so we can just make it kind of narrower. So now we are going into the algorithm. So I will just track this once or twice, and then we'll kind of stop, tracking the actual algorithm. So the first question to ask is whether Q is empty or not. Okay, we are looking at this part of the algorithm, and Q clearly is not empty, has got 2 elements. And then the next one here is very, very important. We are not just randomly picking a vertex out of Q. We're picking a vertex out of Q such that it has the lowest L value. Initially, it doesn't really matter because vertex C and vertex E, they both have an L value of 0. So it really doesn't matter which one you pick. But later on, it really matters. So at this point, okay, we can pick, this is the graph that we are looking at. Vertex C has an L value of 0. Vertex Z also has an L value of 0. So we can pick either one. I'm going to pick E. Okay, so so we go to the trace here, and then we say, okay, I'm picking vertex E as my first vertex to explore. So Q is now becoming just C itself because E is gone. Okay, And now it's time to explore all the edges going into E. So going back to the graph here, E has got one single incoming vertex, which is BE. Okay, so we go here and then we say, okay, we are going to examine the edge BE. We are not necessarily adding it to E prime. We have to make a decision later on. So once we pick BE as the incoming vertex to vertex E, then we have to look at the graph and go like, okay, what is the proposed value of L of B? In other words, am I getting a shorter path this time? In other words, if I want to go through E to go to a destination from B, what would be the cost of that path? What is 1? It will be 1, because L of E is 0. The edge BE has a distance of 1. 1 plus 0 is 1. So now the question is that less than what B has at this point as an L value? B has an L value of infinity at this point. 1 is less than infinity. Okay. So we, in the algorithm itself, we are now evaluating this particular conditional statement. Okay. We are basically asking, is L of E plus D, and then the edge that we're looking at is BE, is it less than infinity? Okay, and the answer is, yep, that's less than infinity. So then we have to perform all of these steps. The first step is to update the L value of the vertex that we are looking at, which is B. So we look at column F, and then we go like, okay, it's not infinity anymore, it is now 1. Okay, the cost or the length of the shortest path from B to a destination is just 1 at this point. But we got a few other things to do. So let's look at the algorithm. We have to remove any edges in E prime that starts with E. Okay, so we go to the trace and we look at E prime. E prime is empty. There's nothing to remove from E prime. Cool. Okay, but technically speaking, we are still quote-unquote updating E prime, so I'm going to put an empty set here. If you don't, that's fine. I'm not going to take any points off. Next step is to update E prime again, but this time we are adding an edge to E prime. So this one is important. This one, if you miss, I'm going to take points off, okay? Because we are adding this edge BE to the set of E prime. In other words, BE as an edge is now on a shortest path of some vertex. Okay, to be more specific, it is on the shortest path of B to a destination. Is that okay? Then we go back to the algorithm, and then the next thing we do is to add B itself to Q. So the idea of doing this to Q, okay, so Q now has BC because we're adding the vertex B to C. The idea of doing this step is because the L value of B just got updated. It just got smaller. And that can potentially trigger the updates of everybody else, or the vertices that are all going through B. So that's why I'm adding B back to Q and saying, hey, let's reconsider all the vertices that have edges to go to B, because they might get a shorter path because of this update. Is that okay? All right. Okay. B is the only path, I think, or the only edge going into E. So we are done here. So now we are back to the outer loop, which is here. Q is non-empty, so we have to select another V again. So now we have to pick another V out of B and C. Out of B and C, we want to pick the one that has the smaller L value. B has an L value of 1. C has an L value of 0. So we have no choice but to pick C. Okay, so we pick C, which also means now we have to examine all the incoming edges to C. So when you look at vertex C, has got 2 incoming edges. It doesn't really matter which one you look at first. That order is not important. So we'll look at FC and then we'll look at AC. So getting back to the trace, we are now looking at FC. Okay. And when we look at FC, what we are really considering is, if I go from F to C, is that a shorter path for F to go to a destination? Well, at this point, f has a length to the destination of being infinity. And with this, because L of C is 0, plus the distance of FC, which is 1, that is 0 plus 1, which is 1, 1 is less than infinity, yep, we just found a shorter path to go from F to a destination. So in the trace, we're going to do all the updates, just like the other one. First thing we do is we update the value. So we look up F in this case. So F is right here. It has a L value of 1. And then on the next row, we remove every single edge going from F to something in E prime. Well, we don't have anything like that, so we just say, okay, it's the same as before because the quote-unquote removal did not actually remove anything. And then we have to add this new edge into E prime. So E prime now has BE, and we are keeping that, but it also has FC in it. And then the next step is to add F into the set. I forgot to do one thing. Once I pick C, I have to remove it from Q. So at this point, then we'll have B and F left in the set Q. Is that part okay? Cool. All right. And then the next step we have to do is to say, okay, are there any other incoming edges to C? Yep, there's one more. You can see AC, is also an incoming edge. So we now have to look at AC, which has a distance of 4. Okay. So we say we are now considering the edge AC. Well, as it turns out, A has an L value of infinity at this point. And when you look at the distance AC, it has a distance of 4. C has an L value of 0. 4 plus 0 is 4. 4 is less than infinity. So we better update this one. So we say, okay, let's update this one to 4. The L value of A is now updated to 4. And then we go to do the rest. Okay, any edges starting from A has to be removed from E prime because we just found a shorter path to a destination. Well, fortunately, there's none at this point. So that means it's going to be the same as before. But we also have to remember to add this edge AC to the set. So now the set includes the edge AC. We also have to remember to add A to Q because its L value has just been updated. So now Q is A, B, and F. We go back to ask another question. To ask the question, do we have any other edges going into C? And the answer is no. It only has got 2 incoming edges. So we are now done with the for each loop, and we're going to go back up to the while loop. So we're going back to here at this point. Okay, Q is not empty; has got 3 vertices. So out of all the vertices in Q at this point, we need to go find the one with the least L value. So going back here, okay, we have A, which has an L value of 1. We have B, which has an L value of 4. Excuse me. A has an L value of 4. B has an L value of 1. F also has an L value of 1. So once again, we have a tie. You can choose B. You can choose F. Doesn't really matter which one you choose. So I'm just going to pick the one that most people would not choose. I'm going to choose F first, because I know most of you guys are more kind of sequential. Okay, you see B, you go pick B, but I'm going to pick F. So picking F as the new vertex. So what we're doing now is to say, okay, first thing is to remove F from the set Q. Okay, and then we have to look at all the incoming edges to F. So you look up F, which is here. It has got 3 incoming edges. It has got BF, EF, and DF. Okay, we'll go in this particular order. We'll first consider BF. And this is why the column for E can be handy, because this way I'm not going to forget which edge we are looking at. So from here on, it will look a little confusing, especially when we need to look up the values. Do you guys want me to just kind of copy everything here? No? Yes? Maybe? No?
Starting values?
I'm trying to think of a way to do all the copying, but without actually, manually copying.
Put them in a different color, like red. Put them in a different color, so we know they're.
Can you make another line, like the first one, and just put the values there?
Yeah, but then I have to copy every single time, I copy the whole row. I'm trying to use a lookup feature to look up the last update in that row.
But I mean, you could just have like.
I'm trying to be lazy.
You gotta just go up to the top of wherever you're looking at.
Yep.
You could pull each of the columns down after you've gotten a number different than.
But that takes work on my part.
You can store it in memory.
Hmm?
You can store it in memory. Your own brain.
I'll just kind of look up the columns as we go. Okay. All right. So we want to look at the edge. Yeah.
You could create a row right under, in row 2, you could add a row, and in that row you could keep the value, the updated value. Like,
True, but then I have 2 places to update something. Yep. But that will work. Okay, so, back to here, BF. Okay, so we're looking at the edge BF. And the first question is, am I going to update, L of B because of that? Okay, so when you look at BF, okay, F has an L value of 1, okay, because that's what we can put into L value of F. BF has a distance of 4. 4 plus 1 is 5. And the question is 5 less than the current L value of B? We know the current L value of B is 1 already. 5 is not less than 1. So we're not going to go through the then part of the conditional statement, which also means there's nothing to do. Okay, if there's nothing to do, we move on to the next incoming edge to F. We'll pick the next one being EF. Okay. So when you look at EF, there's also nothing to do because E itself is a destination, which is guaranteed to have an L value of 0. Okay, so there's nothing to update. We're not finding a shorter way to go to the destination. So finally, we move on to DF. Okay. So when we look at DF, we go like, okay, now we got something to do because the current L value of D is infinity. And at this point, the L value of D is going to be 2 plus 1, which is 3. So we're going to update it. So when we go into the then statement, we got several things to do. We got exactly like 4 things to do. So the first one is to look up column H, and then we update the L value of D to be 3 in this case. Second thing we have to do is to remove any outgoing edges from D from the set E prime. There's none here, which means there's nothing to really remove. And then the third thing we have to do is to add DF as an edge into the solution set of edges. So DF is added to E prime. And then the fourth thing to do is to add D to Q. So now we have ABD in the set of Q. Are we doing okay so far with this? And at this point, we have looked at every single incoming edge to vertex F, which means we are now ready to move on to the outer loop. Yep.
So in the assignment, you said to use a new line anytime it's updated.
Mm-hmm.
So for the things that were supposed to be removing something that weren't, I didn't put a new line. And for the when you are checking between.
Yeah, that's fine. So you're missing this row, right? You'll be missing row 22.
And then 18 and 19, I was also missing just because.
18, 19.
Yeah, just because I wasn't checking for.
Right,
there was no
yeah.
update, so.
These 2 columns are really just for your purpose of tracking stuff. So, if you don't track, these correctly, that's fine. But QE prime and then the L values are the ones that I'm looking at. Okay. Okay, so now we're back to the outer loop, which means we're checking is Q empty. Q is not empty, has got 3 vertices. So of the 3 vertices, we have to find the one that has the least L value. A has an L value of 4, B has an L value of 1, and then D, which is what we just updated a little bit earlier, has an L value of 3. So the one with the L value of 1 is going to be the one that we want to pick, which is vertex B in this case. So we choose B to be the one from Q. So that means Q itself also has to be updated to be just AD because B is now removed. So now we have to look at all the incoming edges to B. And if you look at B, it has one single incoming edge from A with a distance of 3. Okay. So now we go here and then we say, okay, we got the edge of AB to consider with a distance of 3, if I remember correctly. Yep, AB has a distance of 3. So now the question is, am I finding a shorter path to A? A has a shortest path with a distance of 4 at this point. B has a shortest path of 1, a length of 1 of the shortest path. So 1 plus 3 is 4. In other words, I have found another path of exactly the same distance from vertex A. Do we update? According to the algorithm, do we update?
No.
Nope, we do not update, so we are done. So that's the only incoming edge to vertex B, so that means we're done with the for loop. So we are now going back to the outer loop. We check Q. Q is not empty because Q has 2 elements left, which is A and D. So of these 2 elements, we have to pick one. A has a L value of 4. D has a L value of 3. So D is going to be the one that we have to pick. So once we pick D from the set will only have A left. And now we have to look at all the incoming edges of D, which is none. D has no incoming edges. That makes it easy, right? Okay, so now we're done with the inner loop. We go back out to the outer loop. So we only have one vertex left, which is A. Which one has the least L value? A. Okay. So we pick A over here, and then Q becomes empty, but we cannot stop yet, okay? Because we have to look at all the incoming edges of A to see if that will trigger any actual updates. So now we look at vertex A, which is this one here, has got 2 incoming edges. We can look at EA first, okay? So we look at the incoming edge EA first. Okay, it's EA. The incoming edge EA is, we don't really have anything to consider because E is a destination already, which is guaranteed to have an L value of 0. This cannot be a shorter way to get to the destination. Okay, fine. We look at the next one, which is GA. And then we look up the L value of G first. The L value of G has not been touched, which is still infinity at this point. Okay, so that means we are going to have to update it now. So now we're going to update the L value of G, which is column K, to, okay, so A has an L value of 4, and this is 4 also. 4 plus 4 is 8. So the L value of G is now updated to 8. And then we have to do all of that stuff to update E prime. There are no outgoing edges in E prime at this point from G, so the so-called subtraction does not do any actual work to this set. But we do have to add the edge at this point. So GA is now added to that particular set. The next thing we do is we have to add G to the set Q. So Q is no longer empty. It has G in it. And at this point, we are done with the inner loop because in this graph, we only got 2 incoming edges into vertex A. We have now considered both of those incoming edges. So we go back to the outer loop, which is the while loop. Q is not empty at this point. So we have to pick G out of that set. The set once again becomes empty. And then we have to look at all the incoming edges of G at this point. G is right here. It has got 1 incoming edge, which has a distance of 2 from C. So we have to look at CG as an incoming edge. This one is trivial to consider as well because C is one of the destinations. It has an L value of 0, so we cannot possibly be finding a shorter way to do it. So that means that it doesn't cause any actual updates. Then we are done with the inner loop. We go back to the outer loop. Q is still empty at this point, and that ends the entire algorithm. So the question now is, okay, so if this is the end of the entire algorithm, what is the actual result? Well, there are two things that are the actual results. One is we actually know the length of the shortest path from every vertex to a destination. If you look at the L values, each one is indicating the length of one of these shortest paths from that vertex to a destination. Okay, now the way I said it is because to indicate that there might be multiple paths from a vertex to a destination and they're all the same. That's okay, okay? But E prime is only tracking one. So when we look at this E prime here, it is indicating that BE, FC, AC, DF, and GA are the edges in this solution. Which also means if you go back here and you highlight those 5 edges, it becomes a subgraph of this original graph that only has shortest paths in it. And that is guaranteed to be a forest. In other words, you cannot find, you can only find trees in that subgraph. So are we doing okay, or yep?
Are we supposed to turn that last part in, the highlighted graph part?
You don't have to turn that in.
Okay, that's good because I didn't.
Yeah, that part is really just kind of looking at E prime. So if your E prime is correct, you got it. I mean, it's just when you look at E prime, it is just an alternative representation. It's just kind of like a more spelled out version of the graph. But looking at this, and just highlighting the edges, can be good for people who are more visual, so they can actually see, the shortest paths from each vertex to a destination. Yep.
So that would just mark up just the shortest path. You could like essentially rewrite this, maybe like to show, just it would. I guess I'm confused what you're saying. The E prime is just the shortest path, right?
E
That's
prime
just like the
is
shortest path from C to E, or
E prime. Okay, if you construct a new graph, say call it G prime,
yeah,
which has the same vertices as the original G, but E prime instead of E as the edges, that graph will only consist of shortest paths from each vertex to a destination.
Okay.
So in this case, E to B would be secluded from the other.
E
part.
to
Or B to E in it.
B to E. Well, if B to E is not in E prime, B to E is in E prime, so B to E is in the solution graph.
So it'd be, but we'd kind of have 2 separate parts to it because B and E would be secluded, and all the other parts are connected to C.
Let me see if I can do this. Okay, I'm gonna. Yeah, go ahead.
I was gonna say, could we show that on the tablet to see, if for those of us who are
Yeah, but moving a clip, art or a clipped image from here to the tablet is actually more work than
oh yeah,
it's worth. So I'm gonna do another trick here. I'm taking a crop of a crop. And I'll use another tool to do this. I'm gonna save this to that, and then we'll use another tool to do this. We'll use Inkscape. Inkscape is pretty good for this sort of thing. Okay. And then we'll import the PNG from the temp folder. It doesn't really matter. Okay, we'll do this part. Okay, so it's actually easier this way. I just have to use my mouse as a pencil this time. Okay, so we'll use one of the pencil tools. And what color? Okay, we'll use red here. There we go. So I'm gonna highlight the actual graphs. So we'll go back to the solution BE. Okay, so we'll add BE. Okay, that's not the color that I want. Okay. Set stroke. I have to select it. There we go. Okay. No.
There's no like paintbrush or anything.
Sorry?
There's no like paintbrush or anything that.
No, I know how to do it in other ways. I can look at. Okay, I know how to do this. What we need is okay, view. Okay, let me draw the arrow first, draw the line first. Then we can right click and click fill and stroke. There we go. So we can now specify the fill to be red. There we go. But it's filling, so we need to look at.
Is there a spray paint tool? Is there a spray paint tool you can use?
No, it's not a graffiti tool.
No, is there one?
No, I'm just kidding you. There we go. We got the red. It's not thick enough?
Yeah, we can.
Above the eraser.
There we go.
Yeah.
Cool. Sorry? It's above the eraser?
There's something above the eraser.
Looks like green.
Looks like a spray
canopy.
paint.
Oh.
There's also a bucket.
Yeah, this one? Yeah, spray objects by sculpting or painting. Somehow I don't think that's what we need. Okay, so B is here. Okay, so let's look up the other ones. FC, so we want to highlight here FC, FC, which is this one. Okay, and it doesn't keep the,
That's why.
well, I'm pretty sure there's a way to do it.
Yeah, it gets
There we
the point
go.
across.
I think the way to keep it is to click the tool itself first, and then select what we want. I think that will keep it for the next one. We'll see. Okay, and then AC. Okay, so we got AC. All right. DF. Okay, so we have DF, which is this one. If you have not used Inkscape, try it out. You can use it for a lot of different things. It's a pretty cool tool.
It's open source, right?
Yep, it's open source, and then we have GA. So that's this one. Okay. There's definitely a way to kind of keep the setting. I just do not use it very often. There we go. All right. So when you look at the red lines, that's the subgraph. In this particular case, we have red lines connecting every single vertex, which means every single vertex is reachable to at least one of the destinations. Yep. Go ahead.
Can it be said that anything coming out of a destination will never be part of a solution set using Dijkstra's algorithm?
Say that one more time. Anything coming out of a destination
Out of a destination part of the solution set?
will not be a part of the solution. It depends on whether that edge is 0 or not.
If it, oh, okay. I mean, if it,
You can have two destinations. Well, okay, if it's a destination, then it's already a destination. But you're right, because it has to have incoming edges. So it depends on whether that particular vertex. Okay, I think I know what you're talking about. Okay, so I know. Okay, so you're looking at, okay, so let's say D is a destination. Okay, but what you said is not entirely true because it depends. Okay, so let's say D, which is a destination, has an edge to A, which has a distance of 20. Okay, but that does not automatically guarantee that A is not going to be a part of the solution because it also depends on whether there's an edge here.
I was talking about just the edge going from D to A.
There's just the edge from going to.
Any edge coming out of a destination wouldn't be part of the solution set.
It would not. Yeah, correct. The edge itself would not be a part of the solution. Correct. Yep. That is correct. So, but in this case, we got we have two trees in this case. Okay, if you look at it from the tree perspective, there are two trees. One is rooted at vertex C, the other one is rooted at vertex E. The one that roots at vertex E is a very simple tree. It has got the root and one vertex going into the root. The other one, the one that's rooted at C, has two edges coming out of the root. One goes to A, the other one goes to F, and then the one that the subtree that roots at F has a single vertex of D hanging out of it, and then the one that roots at A has G hanging out of it. But it is still a forest. Okay, so this is the solution of Dijkstra's algorithm, is always a forest. Which is kind of cool because now you can apply tree type algorithms to the solution of Dijkstra's algorithm for whatever you need to do. Yep.
So would G prime include the values of the first of like 4, or would it be like the L values that we got from
G prime is okay. So when you look at the description of the algorithm, which is in the Firefox tab. So when you look at the solution is G prime. So what is that telling you? Well, G prime is a two-tuple which consists of V and E prime. Yep. So that's basically what it is. That's your solution graph.
So like if V would be like A, or V would be like VE?
V would be the same as the original graph's V. So the graph is originally, G equals to VE. The same V is used over here. So the only difference between G prime and G is instead of using E, which is a superset of E prime, we only have E prime. Is that okay? G and G prime are almost exactly the same, except G prime only has edges that are parts of a shortest path.
What was V again?
V will be the set of all the vertices.
A, B, C, D, F, G.
In our homework assignment, there will be A to G. Yep.
So in G prime, do we have, for the E prime, do we have a distance function for that too?
Well, the distance function would be the same as the original distance function D. So we are not changing that. We are just trying to remember, which edges are a part of the shortest paths. But the important part here is when you apply Dijkstra's algorithm, you're not finding a shortest path from one vertex to another vertex. You're finding the shortest path of every single vertex to a destination. So that is kind of the interesting aspect of Dijkstra's algorithm. Yep.
So when A, B, and AC have the same value, could you, if you wanted to, just swap them out and the solution would still be viable? Or you would just, if they're equal to each other, you just leave it as is?
You mean if two edges are the same?
Yes.
Okay, so tell me again, which
We'll go
two?
to the sheet.
Okay, so tell me one more time what you were talking about. So
The spreadsheet?
in the spreadsheet?
Yeah.
Okay, so let's go look at the spreadsheet.
A, B, and AC, they both equal to 4.
A, B, and AC. Okay, so but they go to different destinations, right? So when you look at the graph, A, B, and AC, A, B, and AC, which one do you think you want to take? Because we are trying to find the shortest path, right? So is AB on the shortest path, or is AC on the shortest path? Are they both on shortest paths? Only one of them is on the shortest path. Remind me again, what are our destinations? Which vertices are bathrooms?
C and E.
C and E are bathrooms. You're at location A, and you cannot hold it anymore. You need to find the shortest, the bathroom that is closest to you. Which route are you going to go? Are you going to go straight to a bathroom at C, Or do you want to get a detour to B and then F and then go to the bathroom? Or detour to E.
And they're both 4, so.
Okay. So in that case, you can choose either one.
Okay. But the algorithm doesn't specify, but you could.
Correct. So which one is in E prime depends on when we explore which one we pick to explore first. Is that okay? That's a good question. So at which point of the algorithm would we have made that difference? Because at this point, the algorithm keeps AC and not AB, right? So at which point in our algorithm did we make the choice that would turn it this way instead of choosing AB as the shortest path? We added AC early here, okay? Which means the choice to explore C ahead of E is the reason why we have AC in the solution set but not AB in the solution set. If we had chosen E to explore first out of Q, then we would have the other shorter path. They're the other shortest path, but they have the same length. Yep.
Could we change, like, if we were programming this, we could probably change the algorithm so that if they were equal to, then it would add both solutions to E prime?
Then your solution would no longer be a tree. Why do you want to add both to the solution?
So that you have options that if they're both the same distance, then maybe like if you're using Google Maps and you have two solutions that are the same.
Aha. Well, I like that idea. You're basically making sure that you do not have what we call critical paths, which means okay, a critical path is one where if a particular edge goes away, things become disconnected. So you basically are trying to make sure that you have multiple ways to get to the same point, but also at the same cost, right? So that's not a bad idea. But typically in a shortest path algorithm, we just find a shortest path instead of finding also alternative paths of exactly the same length. When you have one of the edges disappearing, like there's road work, then you basically remove that edge and then you rerun the algorithm again to find the alternative path. Okay. Any other questions? No questions? Okay, what do you think of the time complexity of Dijkstra's algorithm? How bad can it be?
V squared.
Okay.
That's according to Wikipedia.
Depends on
Okay. But why is that? Okay, so what is the worst case scenario of the Dijkstra's algorithm? In other words, how much time does it take to run this particular algorithm as proportional to the size of V or the size of E? Okay, so you can use any equation involving the cardinality of V and the cardinality of E. So what do you think is going to be the upper bound of the time complexity of the Dijkstra's algorithm?
It has to do with the number of incoming edges to each destination, right?
Yep. Okay, so that means the upper bound is going to be No, you got it. You said something about the incoming edges, right? So it is about edges and not about vertices. So that means the upper bound time complexity of Dijkstra's algorithm is proportional to the cardinality of E, uppercase E. The number of edges determines the worst case scenario. Is that okay? Okay. So any other questions about the Dijkstra's algorithm? Nope. No questions. Yep.
So this is pretty much what we're gonna have on the test.
Yep. On the test, there will be at least one, possibly two or more questions on Dijkstra's algorithm. I typically ask proof questions, regarding algorithms too. So you have to really understand the algorithm well to answer those questions. Yep.
Is the final the same length as the midterms, or will there be?
No, it's longer. The final exam is 2 hours long. So for this class, the final exam starts at 8 a.m. on next Monday. So exactly 1 week from today, minus a few hours.
So would it be like 7 questions, or I'm trying to get a gauge of like how many questions?
Oh, okay. So to answer that question, we can go to the share folder because I have all the previous exams, put into one location. Almost all except for spring 15, it's in here. So there's a folder called old exams or old final exams. This is for spring 17, which was an evening class. And let's see. So 1, 2, 3. I think there were only 5 questions. The number of questions, is not necessarily, indicative of, how much time it takes, because, some of these questions can take longer to answer, like tracing the algorithm. That obviously would take a little bit longer than some of the earlier questions in exam 1 and exam 2. But there will be some proof questions too. So this is from spring 2017, which is just the last semester. I taught the class in a slightly different order. In terms of types of questions, it will be about the same kind of questions. Like in this case, the question is sequentially in each row include a line number and the effect of that line. Basically, it's the same kind of trace as what you did in your homework assignment, except this one applies to the A-star algorithm, which we have not talked about and will not talk about in this class. There's just not enough time to talk about it to include it in the exam, so I'm not going to put it in the exam.
Yeah, I was wondering why I didn't finish your
Yeah, because I was thinking like, no, there's not enough time to actually finish the algorithm. Yep.
Will we go over some sample problems tomorrow on the next class, or?
Yes. Well, today we still have a few, like 20 minutes left. But yes, but on Wednesday we'll also go through some of the exam questions. Okay. So the question number 1 is kind of similar to your homework assignment. In other words, you need to be prepared to trace the algorithm like the homework assignment. Okay. You can almost be guaranteed that it won't be as simple as the homework assignment. There will be something like the example that we went through last week, where the L value of a particular vertex got updated more than once. The first time is when we found a path to the destination, and then the second time is when we found a shorter path to the destination, to a destination. So you kind of have to think about, okay, how do I construct a graph like that, to kind of as an exercise. But you can always go through the example in last week. Okay, question number 2. Using the graph in Q1, change only the heuristics so that the shortest path is not found, blah, 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 blah. So this is kind of the question where, I refer back to the graph in a particular question and say, change certain things so that, da, 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 da. Okay, for instance, in the homework assignment, I might ask you, change the distance of one edge so that this particular edge will now be a part of a shortest path. Okay, yep.
What are heuristics?
Huh?
What are heuristics?
We are not going to deal with heuristics because we are not dealing with A-star.
Okay.
So we only need to know about heuristics when we use the A-star algorithm. And since we have not talked about the A-star algorithm, we're not going to talk about heuristics. But the type of question is, we refer back to one of the other questions and say, okay, change one thing or a few things so that it has these properties. Okay.
So we wanted to know that we could go back to previous videos of the previous semesters.
Oh yeah. These are all open already. Yep. You can print these out and bring with you. But since this particular one only deals with the A-star algorithm, it's not going to be helpful. In terms not for exactly for the test, but in terms of type of questions, it will still be helpful. Question number 3 is talking about a function, injectiveness and surjectiveness. So definitely, that is something that is related. But when we convert this into a graph representation, I have not really talked about the in degree of a vertex. So these questions would not be asked. In other words, I go by what I taught this semester. The questions for your final exam is based on what I taught this semester and not based on the past exams. So some of these questions in past exams would not be relevant. This also would be a good time to illustrate what I did not talk about that is a part of the curriculum. In other words, why Tech wants the semester to be 20 weeks long instead of 16.
20 weeks.
Oh, at least 20, if not more. Most other professors are going like, oh, I'm so ready for winter break. I go like, no, I need winter break to cover more material. Okay, so there are a few things, just so that you know what I have not really talked about that may be important. Okay, the first one is called relations. Obviously, these will not be in the final exam because I did not talk about these things. So relationship is important because, well, it is in the curriculum, probably without the ship. Okay, so they're called relations. Okay, relation is like less than, greater than, equal to, how a particular value relates to another value. Okay, we have not talked about it, but there are some terms that is kind of useful in that, in that topic. The one thing, the application of relations has to do with ordering. In other words, if you're given two things, okay, and you ask which one is better, okay, it's an ordering question. But it's not always the case where you have what we call total ordering, which means you can given any two things in a set, you can always say, okay, this is greater than the other one. There are cases where given two things, you don't know the order. Okay, you don't know the ordering. So that's the importance of relation is, do you have something, an evaluation function that establishes what we call total ordering amongst all the things within a set, which also means given any two things from the set, you can always compare. Okay? Now integers is totally ordered, which means give me any two integers, I can tell you whether one is greater than the other one or they're equal. Okay, I can give you all those answers. So that's the importance of the relations topic. The second one is called recursive relations. I cannot spell. Recursive definitions. Okay, we'll just call it recursive definitions. So it's a way to look at recursive algorithms and predict the time complexity of those algorithms. So with binary search, okay, binary search has a time complexity of the log of the size of the array, which is great. Linear search, on the other hand, has a time complexity that is proportional to the size of the array. Then you go like, yeah, but there's no one who can write linear search as a recursive algorithm. Yes, it can. Okay, and it can be done in a way that can be analyzed by those particular theorems, but we haven't really talked about those. And then the next one is called time complexity, which is kind of important, but I didn't have enough time to go over that one. Time complexity has to do with the big O, big omega, and big theta notation. So big O of n, big omega of n, and then big theta of n. One is the upper bound, one is the lower bound, and one is the kind of the average, or the guaranteed time complexity. So time complexity is interesting because it is telling you if the algorithm takes this much time for a problem size this big, if I double the problem size, how much time is the algorithm going to take to solve the problem? So it's not a question of how much real time it takes, it is just a proportion. If you have a slower computer, it is just proportionally slower. If you have a faster computer, it is just proportionally faster. But we are more interested in how the time requirement is going to change when the size of the problem changes. Is that okay? We're looking at the shape of the curve, but not so much how the scaling is done. Yep.
For time complexity, did you teach that last semester by any chance? Or were you able to cover it?
I was able to cover all of these topics in the previous semester.
Do you remember where in the semester, if I had to try to track down your old YouTube video, you actually covered that?
I can look up my Moodle class because I follow the same sequence in the Moodle class. So I can give you a list, like, you know, the sequence of the topics introduced last semester.
Or even if you could share like the Moodle notes for that.
Yeah, I can do that.
Awesome.
Yeah, Moodle is going to go away, you know, in January, so I have to print it out and then put a PDF on this side. Yep.
Pretty unrelated. The final, is it cumulative or is it just new stuff?
Mostly new stuff, but there may be questions of older material. So surjectiveness, injectiveness, you know, the whole notion of functions and stuff like that, you know, those will all be in it. Knowing how to prove by contradiction and prove by induction is going to be important as well. Okay, so the other one is called predicate calculus. There we go. So predicate calculus is kind of interesting because it is a continuation of the discussion of propositional calculus or propositional logic. The one thing that propositional logic cannot do is the use of quantification. In other words, you can say, you know, so with all the P, Q, R, S, you know, P, Q, and R, S, T, you know, with all the variables in predicate propositional logic, you cannot have quantifiers. In other words, you can say P is the same as TAC is not a good teacher. Okay? And Q is Professor Fox is an excellent professor. And then R is, you know, Subsidiary is a very humorous, you know, professor, and so on. But all of these are applying to individuals. In other words, you cannot say all professors are blah, 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 or there exists at least one professor who is blah, 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 blah. That ability does not exist in propositional logic. But predicate calculus is an extension on propositional logic where that can be expressed. So that is really kind of cool in many ways because now you can specify rules. You can specify rules like every Jedi has a lightsaber. Okay? And then you can specify individuals. You can say Luke Skywalker is a Jedi. And then the engine itself will automatically be able to prove that Luke Skywalker has a lightsaber. Is that okay? So that's the power of predicate logic, is it can be used as an engine to do deduction. It is not just proving a particular theorem, it can find things that fit a particular description. Ancestry is the other one, you know, that is commonly used in examples of predicate calculus. So it can basically specify ancestry as X is the ancestor of Y if and only if the following. Okay? So you can have several things. You can say X is a parent of Y. Okay? If X is a parent of Y, naturally X is an ancestor of Y. But you can also add a rule to introduce a Z. So you can say X is a parent of Z, Z is an ancestor of Y. And now X is also an ancestor of Y. But that is recursive. In other words, the definition of ancestry can be recursive. And then when you enter it in the database and say, okay, Mary is Jane's mother, and so on and so forth, then the database can now figure out, and you can ask a question and say, list all the ancestors of Peter. Then the engine can go through, you know, the necessary, you know, logic to find all ancestors of Peter. Or it can say, find all descendants of Jane. It will find all the descendants of Jane based on the rules that you specify. So that's predicate calculus. On the other hand, you know, since I did not, you know, put any time on these particular topics, I felt that I was able to spend more time on the topics that we did cover, which is kind of a trade-off. But I do want to make it, you know, clear that, you know, we did not cover some of the topics in the curriculum, so that when you have spare time, you know, look up these things, you know, that might be useful when you move on to a 4-year university. But are there any questions about the things that we did talk about in this class? Of all the things that we did talk about in this class, I think the most important parts would be set theory, the notion of functions, how to prove, okay, you prove by contradiction, prove by induction, Those are all important topics. Probability stuff, discrete probability is kind of useful too, but you can get more of those treatments from statistics classes too. But the proof techniques, are really kind of important. Is that okay? Yep.
Will we have any probability questions on the final?
Probability questions?
Like the permutation?
I have not thought about that yet. So potentially yes. Potentially yes. Okay. So getting back to graph theory and stuff like that, that thing is, it's also kind of important because finding the shortest path is kind of like a AI type of thing, at least in the past. It's also something that I did, for my dissertation. In my dissertation, the only thing that is changed is the transitions or the edges are probabilistic. Okay, if you are, let's say you're in vertex B, okay? If you're in vertex B, if you make a decision to go to F, there's a 75% chance that you actually get to F. But there's also a 25% chance that you accidentally end up in A, for instance. So once you introduce the probability or what we call the stochastic, okay, that's the really awkward name for probabilistic. So once you introduce the stochastic nature into state space search, as it turns out, every single algorithm that we know is not usable anymore to find the quote-unquote shortest path. Because just to define what is the shortest path becomes difficult. What is the length of the shortest path when things are probabilistic? Do you see how that can be a little bit hard to define, just to define what is the shortest path?
Could you do worst case and best case scenario?
You can.
Do like an average of that?
Nope, you have to look at the probability. You're basically looking at the probabilistic nature. You can do it by simulation, for instance. You can say, okay, I'll just do it by simulation. Wherever something is probabilistic, I'll just do simulation, and with enough averages of simulation, you get the quote-unquote, the collective average cost of a particular decision. If I choose to go this route, okay, what is the cost of that? If I decide to go this route, what is the cost of that? Yep.
What would that be modeling? Like, in what scenario would a path be?
I like that question. Okay, so the question is, why would you introduce probabilistic nature when we are just dealing with quote-unquote state space search? Okay, imagine you're a robot. Okay, you're a robot like a Roomba. Okay, and your job is to go through all the rooms, clean up, and then go to a charge station so that you can recharge yourself. Is that okay? Unfortunately, you are dropped into some random place into an office building. And whoever dropped you in did not tell you exactly where you are. Is that okay? But in your memory, you do have a map of every single floor of the office building. Okay? So you look at your surrounding. Okay, you see, I see a door here, I see a hallway over here, I see another hallway over here, another door over here, and so on. Can you figure out exactly where you are in the office building? Maybe, maybe not, because there may be multiple places in the office building that look exactly the same from your perspective. Is that okay? But your objective is, my battery is running low, I need to go to the quote-unquote closest recharge station. Is that okay? So what do? You don't know exactly where you are. You may be here, you may be here, you may be here, because from what you can see, they are all about the same. So what do you do next?
That's a chance.
Now there's a chance now, right? Because if you were here, okay, then the closest charge station is over here. If you were here, the closest charge station is over here. But if you're here, the closest charge station is over here. So now there's that probabilistic nature to it. As it turns out, the set of all the potential locations that you could be in can be considered quote unquote a super vertex in this new problem. And then the transitions become probabilistic because you are trying to disambiguate where you are at the same time as you're trying to get to the closest charge station. And that entire process is probabilistic because there's a 33% that you are here, 33% chance you're here, and 33% chance you're over there. So I found certain applications of that theory, in AI. Sort of.
Each time you move, you reevaluate.
Every time you move, you reevaluate, and hopefully, when you move, you will get more information to help disambiguate where you are, and yet also at the same time getting closer to the charge state. All right, I'll see you guys on Wednesday, and if you might want to study a little bit, quote unquote study, just go through all the material. If you have any questions, bring those in on Wednesday, because that's our last lecture.
I have a question about question 2 on the exam. I just want to understand why I got the marks I did.
Okay, this may not be the right time to do it, because I have a class to go right after this.
Okay.
You can email to me, or you can come to my office hour.
Okay.
Either way works.
Okay.
Okay.
Sorry, I'm blocking you. Your time complexity notes are hosted on Moodle.
Say that one more time?
Your time complexity notes, they're hosted on Moodle, right?